Okay, so let's start. Our first problem will be the chi-square test for independence. Have chi-square test for independence. I want you to grab this data set. So load the data set. It will have four columns, as you remember: the sepal length, the sepal width, the petal length, and the petal width. We don't need the species. We would like to see if the sepal length and sepal width are dependent or independent. So um, take the sepal length and width. Now, these will be obviously numerical values. We want to convert them to categorical values. So split each column, or rather, we should say, convert each column to short and long. You can use 0, 1, 1, 2, anything. Just convert it into two categories, short and long, by comparing to the columns median. Once you do that, these numerical columns will be converted to categorical columns. Afterwards, you can just apply the chi-square test. Okay, once you do that, comment on the hypotheses. That is, whether you should accept them as dependents or not. So take 15 minutes and then we'll do it together. Any questions regarding this? Can you repeat?
I mean, it's okay.
Your Yeah, your voice is breaking today as well. Can you write it in the chat, or you don't have access even today? Okay, so let me know if you're stuck anywhere. Yeah, by the way, I was saying in the chi-square test, use alpha equal to 0.05. Okay, 7:30. Let's start. Confirm if you can hear me. Okay. So let's import the libraries first. We'll need NumPy. We'll need pandas. We may need matplotlib as well, and we'll need SciPy start module. Read CSV URL. Header is 0. We have df.head. So our data set looks like this. We only need the first two columns. So we'll say df is equal to df, and we only want the sepal length and the sepal width. So if we have a look at that, we get these values. So because these are numerical values, we want to convert them to short and long. So we can set short as 0 and long as 1 by comparing with its median. So if we print these, let us say we have df dot sepal length dot median 5.8, and similarly for width we have this. In fact, I think we can also apply it to the entire median. We just have to supply the axes. Yeah, so 5.8, 3.0. So if we do df dot apply lambda x, x is greater than this dot as type int, let's see if it works. Running up here ironically, yeah. So let's do it individually. So we have the length median is equal to df dot sepal length dot median, and we have the width median. Yes, 5.8 and 3.0. So what we're going to do is we're saying I want an additional column. Let's call it only length, and we'll say take df dot sepal length if it is greater than the length median. So if I only write this much, it will give me a new column which will be true or false. For example, if we print this much, we'll get true and false values. But I want 0 and 1 values. So what I will do is convert these to integers. An integer converts false to 0 and true to 1. So if we try now, we get these values 0 and 1. Same thing we'll do for width. We'll say width is equal to df dot sepal width is greater than width median as type integer, and rather than maybe the head we can sample some values, let us say 10%. So we had length 5.8 median and 3.0. So this is 5.1 smaller than 5.8, changes to 0. Width is 3.4 greater than 3.0, changes to 1. So both are working correctly. So now that we have these values, we can create a crosstab. Okay, so our crosstab will have length on one side, width on the other side, and both of them have two values, short, long, short, long. Okay, so essentially a 2 by 2 table for our cross table. So to create a cross table, we can use pandas pivot function. So let me show you pandas pivot table. So what table does is you give it one column from your original data frame. You give it one column to use as the new index, another column to use as the columns, and it will fill up the rest. So for example, if we do pd dot pivot table and we say if I supplied everything, let us say my data is equal to df, the full data frame. I say use the index as use length for index, and I want to use um, width for my this thing columns. And if I just do this much, I receive something like this. So on in the rows, I have length. In columns, I have width. Now for each combination of length and width, it will give me the values for the other rest of the column. So when length is zero, width is zero, by default, the aggregation is mean. Okay. So this is just aggregation. I can pass it like this. So let us say we say agfunc is equal to, let us say mean. What it essentially does is when the for cells that have length 0, width 0, what is the mean length? And for cells with length 0, width equal to 1, what is the mean sepal length? Similarly, for sepal width as well, we have two values, 0, 0, 0, 1, and the other one as well. Now, we don't want this, right? What we want is we should have length, we should have width, and I only want the counts. That is how many 0, 0, how many 0, 1, how many 1, 0, how many 1, 1. Is this part Does this part make sense? Any confusion in the pivot table? Okay, so what we want is I don't want to supply the entire data frame. I'll say only take length and width, take length and width, and don't aggregate using the mean function. Just use the len function, the length function, to count how many rows do you see. So it sees 38 cells where length is 0, width is 0, 42 cells where length is 0, width is 1, and same for the other two. Now, this is obviously a pandas data frame, so let's convert it to a numpy array because it is easier to work with. So we can say cross table is equal to this thing, and then we can print it. Okay, so this is our cross table. Now that we have this, let us set up our hypothesis. So we'll have one null hypothesis. We'll have an alternate hypothesis. We know our alpha value is 0.05. Now, the degree of freedom is rows minus 1 times columns minus 1, right? So in this case, we have two rows, two columns. So we can say, let us say df dot, in fact, cross tabs dot shape. This will give me rows. This will give me columns. So this is essentially degree of freedom still comes out to be 1 into 1. Then let us write the null hypothesis. The null hypothesis says the columns are independent, essentially saying not dependent. And the alternate hypothesis says the columns are dependent. Okay, so let's see if this much works. Hmm, why is it taking so long? Let me refresh. 2 by 2, so cross table. Yeah, so if we print the degree of freedom, it will be 1. So because we know our degree of freedom and we know alpha, we can compute what you wrote in your lectures as chi square 0, chi square u in fact. So this is what you get from the table. That is, if you know alpha and you know the degree of freedom, you can take the chi-square value out of the table. That chi-square value is essentially the PPF of the chi-square distribution. Any confusion here? Yeah. So what we'll do is we'll say chi0 is stats dot chi-square, and we can just use the PPF where we supply q equal to something, and the other thing is the degree of freedom, which is DOF. Now, here's the important part. We have set alpha to 0.05, but this alpha is on the right hand side of the curve, or we can say the greater side of the curve. So, because of that, being on the other side of the curve, you don't pass alpha here, you pass 1 minus alpha here. Okay, if it were on the left hand side, we would pass alpha. Because it's on the greater side of the curve, we are passing 1 minus alpha. So, this gives us this value to compare with, the expected chi-square value. So it comes out to be this much. Now we can compute our own chi-square. To compute our own chi-square value, we will use stats dot chi-square contingency. Contingency essentially the cross table. It you can supply it your cross table and it will compute the expected cross table for you. So if we have SciPy chi2 contingency, okay, so we have these values. It takes the observed cross table. There is a correction term which is actually important in this case, and then we have a function lambda that is residual. It gives us four. It returns four things. The first thing is the chi-square value. Obviously, it returns the p-value. We know the p-value, so we can also compare with the p-value. Your degree of freedom, we already know the degree of freedom, and the expected, I mean, frequency table. So let us pass these things. So it expects the cross table. It returns the chi-square value, the p-value. Uh, it returns chi-square value, p-value, the degree of freedom, and the expected cross table. So if we run this and we print out, let us say, chi-square value and p-value, we get these things, and we can also print the expected cross table. Now, if you were to compute this cross table yourself, and then compute the chi-square values, you will actually find a difference between this and what you compute. Now, let us say we have the expected cross table. Let us manually compare. Let us manually compute the chi-square value. So chi-square is essentially um, observed minus expected. You square every individual difference, and then you divide by the expected cross table values, right? So for example, this thing. You have the observed, you have expected, square it, divided by the expected and sum it. So we can just do a sum at the end. So if we print this, this comes out to be different from the chi-square value we get out of this function. This is because by default it passes correction equal to true, and correction says if passes true and degree of freedom is 1, it applies a correction term. That is why it is different from what we manually compute. So for this session, let us pass correction to be false and see if they are the same. So this time we get 4.256, 4.256. Okay. So now it matches what we manually computed. So now that we have the chi-square value and we have the p-value as well, we can now comment on our hypotheses. So there are two ways to decide on our hypotheses. One is using the p-value. Another is using the chi-square value. So using p-value, we can say if the p-value is less or equal to our alpha that we set, then we reject the null hypothesis, which means the columns are dependent. Otherwise, we say cannot reject the null hypothesis. So that's one. In case of chi-square, you do the opposite. You say if my chi-square value, what I computed here, is greater than my expected chi-square value, this one. If it is greater or equal to, because remember this p-value is the area on the right hand side of the chi value. That is the critical point. Now we are saying if the chi value lies within that area. So if my chi value is greater or equal to chi 0, print out the same thing. So let's see what we get. It says reject the null hypothesis. The columns are dependent. What does this say? It says reject the null hypothesis. Columns are dependent. So if we print these out, let us say we have p-value and alpha. Yeah, so the p-value is less than this thing. Similarly, if we print our chi value and chi 0, it is greater than this part. So in either case, we reject the null hypothesis and we say that the sepal length and the sepal width are actually dependent columns. Any confusion? Okay. So moving to our next problem, let's do the chi-square, the goodness of fit. So just a minute. Yeah, so let's do chi-square goodness of fit. I'll give you a distribution. The distribution will contain the temperature for every day of the year. Okay. We want to comment whether the distribution is normal. Okay. So let me give you the file first. Okay. So see if you can access this, and let's take 15 minutes once again, and then we'll do it together. Okay, so let me give you part of it. So your first step will be to compute the mean and the variance. That is, you are assuming that this is a normal distribution. Then you have to create bins for your distribution. So let us say, in this case, df.temp.mean and df.temp.std is this much. So my mean is around 20, my standard deviation is around 9.5. So I'll say that given this distribution, where should I put the bins, put the dividers in my normal distribution so that I get at least five values within each bin. So for example, starting at 20, for example, okay, for example, we'll say at 5, create the first bin that is minus infinity to 5. Then we'll have, let us say, 5 to 10, 10 to 15, and so on. What you will do then is go to each value and you have to decide which bin does it belong to. You will set them in ascending order. That is, this becomes, let us say, bin 0, this becomes bin 1, this becomes bin 2, and you bin every value. Okay, so it is up to you how many bins you create. So let us say I create 7 bins, that is minus infinity to 5, 5, 10, 10, 15, and so on, so on, so on. And my final bin will be sixth bin, and let us say it's at some value, let us say 40, for example. 40 to plus infinity is my final bin. So I'll essentially have 7 bins, and I'll convert every numerical value to a categorical value within 0 to 6. Once I have that, I have to come now this once I have these bins, I will compute the frequency of each bin. Frequency of each bin. I have to compute this actual frequency with the expected frequency of each bin. Now, in class, if you would remember, when you would create these bins, you would do this based on the area under the curve, right? And you would split the bin so that there is equal area under each bin. So if there is equal area under each bin, you essentially mean that there is equal probability to occur in each bin. Equal probability means that um, let us say I have a total of n entries. And how many bins do I have? Let us say I have this many bins, so this many elements will be present in each bin. So this is my expected frequency. Every bucket in the expected frequency will be the same. So for example, if the length of df is this much and I decide to create, let us say, 12 bins, so I will have this many per uh, basically bin. Okay, everyone will be the same. In this case, everyone won't be the same. In the actual case, this is the expected case. Now you have two arrays. You have actual frequency, you have expected frequency, then you can compute the chi-square value. Does that make sense? Any confusion, anyone? Okay. Okay, so it's 8:10. Let's start. So we have this distribution. We assume it to be a normal distribution. When we assume it to be a normal distribution, we can decide the null hypothesis. Remember that in goodness of fit, the null hypothesis is the opposite. That is, we assume them to be normal. That is, population is normal, and the null hypothesis says population isn't normal. Okay, so we have these things. We'll once again use the same value for alpha 0.05. And because we are assuming it to be a normal distribution, our degree of freedom is 2. Okay, one is for not actually 2. I mean, it is k minus 1 minus p, where p is 2 actually. So k will be the length of the data frame, and p will be 2, one for mean, one for standard deviation. So if we write it like this, we'll have length of df minus 1 minus 2. Okay, so we have this. We can once again compute our chi u. So chi u will be again ppf. By the way, what does ppf do? ppf is the inverse of the cdf. In a cdf, you supply a value and it returns an area. A ppf returns the value that has that area. So you supply area under curve and it will return the value which gives that area under curve. So that is what we want. I'm saying, give me the value that has 1 minus alpha area under it, and given this degree of freedom. So I think it was stats.kite, right? So let's close this part. We have stats.kite, and we can print this. Okay, so this is our initial condition. Now let us do that binning. So we don't need this cell, we don't need this cell. So our mean is df dot temp dot mean, and standard deviation is df dot temp dot std. Now in class, the professor did something strange. He said that I want at least 5 values in each bin. So let me divide the entire data frame by 5. But this will create very small bins, okay, and a lot of bins. For example, in this case, let us say it will return 73 bins, and I don't need that many. And those bins will be very equally spaced. So I would rather have larger bins where I can safely say that, okay, it will probably have more than 5. So let us set the number of intervals as 12. Anyway, we have a year's worth of data. So the data frame has 365 days. Let us use 12, let us say monthly data. So we get the number of intervals as 12. Now, what do we want to do? We want to create 12 bins where each bin has the same area under it. So to have the same area under it, let us say how much area does one bin have under it. So area under, let us say first bin. Area under first bin will be, now remember that the normal distribution is a probability distribution. The area under any probability distribution is always 1, right? So I can just do 1 by number of intervals. This is the area under one bin. Now, because I know the area, I can once again use this ppf function to get the individual values. That is 1 times area under bin, 2 times area under bin, 3 times area under bin, and so on. Correct? Makes sense?
Yeah, got
Yeah. So if we do that, let us say we create an empty list for bins. I say for I in range, I start at 1 and I end at number of intervals plus 1. What do? say bins dot append. Now what do I append? Stats dot norm. We get the normal function, and I want to get, given the area, give me the value. Now what is the area? Area is I times area under first bin. Okay, I times area under first bin. Now what are the values for this normal distribution? The mean in this case is the computed mean. Similarly, the standard deviation is the standard deviation. So this will fill up the bins, and if we print them afterwards, we get these values. Okay. So starting from this to this is the first bin, this to this second bin, this to this third bin, and so on. Final one is infinity because anything below infinity falls in the final bin essentially. Okay. So now what do we have to do? We have these values. We have to categorize them into individual bins. Now notice that the bins are sorted in ascending order. So I can also compare in ascending order. That is, are you smaller than this? If you are smaller than this, then you should be within this bin. If not, compare with this one. And if you are smaller than this one, then you are within this bin. So let us write a function for that. So bin elements. It takes an individual value and it takes these bin values. So what do I return? I say for I comma bin in enumerate bins, if x is less or equal to the bin value, return I. So for example, if I am less than this value, I will return 0. If I'm less than this, I'll return 1. And finally, I'll anyway be less than infinity. I will be in the last bin. Okay, make sense? Notice that I'm returning within the for loop, not outside the for loop. So we have this function. So let us try it out on a single value. So let us say we have bin element, we pass, let's say 7, and we give it bins. Which bin do you fall into? You fall in bin 1. Okay, working correctly. So now we want to apply this function to all the values of this series. So how do we do that? We say df bins, this is a new column, is equal to df dot temp. This is our original column. We want to apply a function on it. Now I want to apply a function to every element, so I'll create a lambda function. The lambda function takes one cell, okay, one number x. I'm I'll pass that x to my function bin elements, rather element. So bin element, I'll pass x and I have my bins. So we have this, and if we once again print some of the values, uh, so let's take a smaller fraction. Yeah, so 10, 5, 2, 2, things like that. Yeah. So now I have the bins. Now I have to create another column which is for the expected values. Okay. So that is very easy. So we can say exp. In fact, let's create the cross table first. Now we have these guys. We have to compute the frequency of every individual bin. Correct? Now let us check another thing. We say df dot bins dot value underscore counts. Okay, so I want to check whether every bin has at least 5 characters. So I'll say this is greater than 5, or maybe greater or equal to 5. This returns an array of true and false values. I want to check whether everything is true. So I'll pass it to all. So it says, okay, every bin has at least 5 entries. So we are good in that case. Next, we want to create a cross table. This time we won't be using a pivot table because there is only one column to work with. So we'll rather use our old function group by. We'll ask it to group the data set based on bins and to aggregate using just count. So if let us say we do this and print the rather let's print like this, print the cross tab, we have this thing. So 0, 27, 1, 35, 2, 37, 3, 31. Okay, makes sense.
Yes, got it.
Yeah. So again, rather than working with the pandas data frame, let's work with a numpy array. So if we do this, it will return n by 1. Let's flatten that. So we have this series of numbers. This is just the count of individual bins. The other is the expected crosstab. The expected crosstab has the same shape as this one, but every entry is n divided by number of intervals. So we can say this is equal to np dot ones like. Ones like essentially says give me an array of ones that has the same shape as the input. I'll pass crosstab as the input and I'll say give me an array of ones. To this array of ones, I'll multiply length of df divided by number of intervals. If we print this, we get these values. Okay, everything has the same expectancy because everyone has the same area under the curve. Correct? Now we go for the chi-square value. Now this time we don't have a cross table, so we won't be using chi2 underscore contingency. This returns a contingency table. This time we have two arrays and we want to compute the chi-square between them. So how do we do that? We use um stats dot I think it was chi-square. So we use this and stats chi-square. It takes f observed, f exponential, the degree of freedom, and x's. So in this case, x's is only one, so we don't have to pass that. So first is f observed. So f underscore obs is equal to cross tab. F underscore exp is exp. In fact, we shouldn't call them cross tabs. Okay, anyway. So cross tabs. Then we have the degree of freedom. DOF is equal to DOF. We computed that earlier. Here, DOF. And finally, there is x's. Now these are flat arrays, so x's doesn't matter. So what do we get from this function? It returns the statistic, that is the chi value and the p value. So we say chi comma p val is equal to this thing, and we can print them. Mm, DDOF, okay. So do we not pass degree of freedom? I think it computes as a delta degree of freedom, adjustment to degrees of freedom for p value. The p value is computed using chi-square distribution with k minus 1 minus. Okay, so this is essentially 2 in our case because it will compute k minus 1 in that way. I don't think we have to pass this. Yeah, I don't think we should pass this. K is the number of observed frequencies. It can compute this thing from summing up all of the values, okay? And I can pass DDOF to be 2 only, right? So let's do it this way. Okay, so I get,
It's yeah.
yeah. So I was saying because it has individual frequencies, it can sum them up, I assume, to compute K, right? Once it has K, it essentially does the same thing, K minus 1 minus DDO, what we did earlier. So we get these values, we have the chi-square value and we have the p value. Now, once again, we do the same check as we did here. We say that If the p value is less or equal to alpha, you reject, otherwise you accept, you cannot reject. Same thing here as well. So let us do this again. You cannot reject the null hypothesis. So the null hypothesis actually said that the null hypothesis said that the population is normal. So it says we cannot reject it. So I mean, we cannot comment whether it is or isn't normal. If we had rejected it, we would say it is definitely not normal. Okay, so it is probably normal in this case. So what does the other value say? So it also says that you cannot reject the null hypothesis. So because I created the data, let me tell you that I actually created it with the same mean and standard deviation. It had mean 20 and STD 10. So the chi-square test is actually correct to say that you cannot reject the null hypothesis. Any confusion?
Yeah.
Okay, so the final part is actually, it was just an introduction in your lectures, cluster analysis. The main part is in the next week, I believe. So in your cluster analysis, I believe the first thing you saw was normalization. You can normalize using standard deviation. You can normalize using the mean absolute deviation. So these are two things. Then you saw various distance functions. So the first one was Euclidean. This is essentially geometric. Then you saw Manhattan. And the third one was Minkowski. Okay, so pretty simple thing. So let us say we have x is equal to np dot random dot uniform, and low is set to 0, high is set to 10, and what does it take? Low, low, high, and size. Yeah. So size, let us say I want 20 values, and I print x. Then I have y is equal to np dot random dot uniform, and this time the low is equal to 0, high is set to, let us say, 1000, or let us say start from 1000 to 2000. So a very large range compared to this one, 0 to 10, and size is set to 20. And we have these. Okay, so if we try to plot them on the same axis, so let us say we give this, and scatter. So you will notice that the scales are different. The Y scale starts from 1100 to 1900, and this scale starts from 2 to 9. If I started this scale from 0, essentially this may collapse. I mean, part of it. Okay. So let us say I said PLT dot Y lim is equal to 0 to 2000. So essentially, this variation collapses to some essence. Okay. So rather than doing this, I can normalize the values up front. So I can say x underscore norm, or maybe let us say, or maybe, yeah, x underscore norm is equal to, what do we do? Every value we subtract the mean, okay, and we divide by the standard deviation. We do the same thing to y. Okay, so let's remove this plt dot scatter xy. Let's keep this as is. And we have plt dot ylim 0 to 2000. And in this case, we have plt dot scatter x norm y norm. So this time the values are around 0 and both the x's are same, minus 1.5 to 1.5, minus 1.5 to 1. This is an additional column too. It is actually here as well, but it's not printed. So this is one way to do it using standard deviation. The other way is mean absolute deviation. So in mean absolute deviation, rather than dividing by the standard deviation, you divide by another number, what you call SF. To compute SF, what did you do? I think it was the average of absolute differences. So it is x minus x mean np dot abs, and then you essentially take the mean. So this I believe is SF. Yeah. So this is your you will divide by this in case for x standard deviation, and you will divide again for y deviation. So let us do that. We have this. Let us write is as XSF, and similarly we'll have YSF. And period absolute, we have Y, and we divide by XS underscore F, and underscore F, and we do the same thing. So quite similar because we don't have any outliers in this case. Okay. So we have normalization. Then again, we have the distance functions. Pretty simple. For example, we have 2 points. Let us say the first point is p0. Let us say is x0 comma y0, and p1 is x10 comma y10. So we have these 2 points. So the Euclidean distance is, I mean, rather than this, let's keep them as arrays. Yeah. So the Euclidean distance would simply be, you will do p0 minus p1. This is the difference. You square the difference and you sum it up. So this is your Euclidean distance. Then in the absolute case, you won't square it. You would just take the absolute values between the two. So Manhattan would be np dot abs, and you would sum it up. Finally, in case of Minkowski, what do you do in Minkowski? I think Minkowski. Manhattan Mass Chebyshev. Yeah, this one. Yeah. So this minus this raised to p 1 by p. So you will say now you only have, for example, in this case, 2 dimensions. So we'll have p0 minus p1, and you again take abs. You raise it to the power p, and then you take the mean, and afterwards you take raise it to the power 1 by p. So in this case, let us say p is 5. Okay, so we have all of these values. Any confusion here?
Now it's clear.
Okay, so that's it for the session. I'll upload the code to the GitHub repository. And for people new here, let me show you the repo. I think we I accessed it several times, but still. So this is the repo. All of these sessions are present here. Any questions before we end?
Hello,
Yeah, hello.
hello. Sir, I have a question, but not related to session. Actually, just want to confirm, like how we can download the admit card for the exam, and from which date I'm able to download it.
Yeah, I'm not aware of that actually. You'll have to communicate with the professor or the other TAs. So as I said in the previous session as well, there are two sets of TAs. One handles the live session, the other handles the exam and the lecture work. So you'll have to contact them.
So, like, I have posted my query on the discussion form. So, is it sufficient, or do I need to share any message to another mail or something else?
How many days has it been?
So actually, just a few days ago, like yesterday, day before yesterday, I just posted my message on the discussion group.
So do they normally reply?
No, no, I didn't get the reply.
No, I mean for previous questions, if anyone else asks, do they reply?
Yes, yes.
Yes, then they will reply to you as well. I think it would be a common query. So other people will
Mhm.
also ask.
Okay. Okay.
Yeah, in case they don't reply, you can maybe fetch the email ID from the professor, or maybe you can contact the NPTEL forum as well. That I am unaware of the details so, and I have posted it on the forum. I am not getting any answers. Kindly help me in this case. They should get back
Okay.
to you.
Okay, sir.
Okay. Anyone else?
No, nothing else.
Okay, so I'll stop recording.